Are we together, members? Are we together? Stephen, are we together? Yes.
Yes, we are together.
Yes. So from here, this one here, up to this point, is L cos theta. This one is L cos theta. Then this one is a combined because it's embedded. So they will move with a common velocity. Now here they will move with a common velocity. They will move with a common velocity. So now we can go on and on and on. We can go on and on and on. So we can say this is after collision. This is after collision. But we know that when you are resolving, so you said resolving along the vertical axis. Resolving along the vertical gives. So when you resolve this one, you resolve the component of L along the vertical. You find that we shall have L cos theta, like we have here. But we know that L is equals to. So when you see from here, this L here is going to be L cos theta plus the height when you are resolving along the vertical. So it's going to be this L is equals to L cos theta plus the height. So which means from there we can now use it even to find the height. So we find that our height will be L minus L cos what? L cos theta. So which means the height h is given by L into 1 minus cos what? Cos theta. Have you seen that, members? Have you seen that? Members, have we seen that?
Yes, teacher.
Yes. So now, remember we said momentum is conserved. If you see our statement from here, a ballistic is a classic example of a dissipative collision in which we are saying dissipative, which means there's a reduction in energy. There's loss in energy. There's loss in what? Energy. Because remember the bullet, this one is at rest. The block is at rest, but it come and then get embedded, then they will move. Then it will start what? It will start swinging. It will start what? Swinging. So that is what we call a ballistic pendulum. A ballistic what? Pendulum. Ballistic pendulum. So we are saying kinetic energy is not conserved in the collision, but momentum is conserved. Momentum is conserved. That's what we are saying. That's what we are saying there. So let's continue with our notes there. So we're saying the device illustrates the law of conservation of momentum and mechanical energy. So write note. The device or the ballistic pendulum. The ballistic pendulum illustrate the law of conservation of linear momentum and mechanical what? Energy. And when I talk of mechanical energy is potential energy. Mechanical energy is potential energy plus kinetic what? Plus kinetic energy. So you should take note of that. So potential energy yes. So mechanical energy is potential energy plus kinetic energy. You should take note of that. So let's now look at what happens before impact or during impact. Before impact is very clear from there. Before impact, during, and then after collision. So let's look at during collision or during impact. During impact. what happens? What happens? That's what we want to see. We're saying that during collision, mechanical energy is not conserved because of friction and other non-conservative forces. Because of friction and non-conservative forces. But linear momentum is always conserved for any type of collision. Momentum is always conserved. Momentum is conserved. So we are saying mechanical energy, mechanical energy, mechanical energy, mechanical energy, mechanical energy, mechanical energy is not conserved because of friction, or you can talk of because of resistance, in bracket friction and other non-conservative forces, and other non-conservative forces. What are non-conservative forces? These are forces which keep on changing. They keep on changing. They are not constant. They are not always constant. Like air resistance, frictional force, they are not always constant. But conservative forces are always constant, like gravitational force, electrostatic force. All these are always constant. So we shall see conservative forces in details. That's the first thing you should note there. Then linear momentum. 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 Remember, my screen is not clear again. Let me check. Okay. Linear momentum is not, it's conserved, sorry. Linear momentum is conserved. In the horizontal direction. In the horizontal direction. Along which there is no external, what? Force. There's no external force acting on the system. There's no external force acting on the system. Good. So we are saying for linear momentum, linear momentum is always conserved. Remember, we are talking about linear, which means we are talking motion in horizontal direction only. Why are we not saying along the vertical? Because in the vertical, there's weight, there's component to do with weight, which means that one will be an external force acting on the system. So whenever there's an external force acting on the system, momentum will not be conserved. Momentum is only conserved if there's no external force acting on the system. So here we are considering only the bullets. We are not considering any external force like weight, like air resistance, like the frictional force. That one we are not considering them in this calculation here. We are not considering them because momentum must always be conserved. So if that is true, so I will take V to be the final velocity. V, let's assume that they will be moving with a final velocity V. So they will be moving with a final velocity V. Or they're swinging with a final velocity V here, from here. As they're swinging, they'll be swinging with a common velocity V. So it's moving with a common velocity V. So we can now say, let's say, if V is the common velocity, if V is a common velocity after collision, after collision, full stop. And the type of collision here is inelastic, members. The type of collision is inelastic what? Is inelastic collision, because after they will move together. They will move together. The bullet get embedded. So which means we shall have mass U plus plus this one. Remember, the bullet, the block is at rest. So which means the initial velocity there will become 0, equals to m plus small m times the common velocity v, So which means I remain with mu equals to capital M plus small m times the common velocity. So which means our common velocity now, if you want us to find the velocity, so which means the common velocity v will be equals to mu over what? M plus small m. So that's the common velocity. That's how we can find the common velocity. Remember, the block was initially at rest. Not. The block was initially at rest. Not the block was initially at rest. So that is it. That is it, members. Are we together, members? Are we together? Brenda, Brian, Emma, are we together?
Yes, teacher.
Are you following me?
Yes, sir, we are following.
All right. So that's,
Excuse me.
yes.
I beg your pardon on the first part of
first
the work.
of the work here. This one. This one here. Okay, we are looking at ballistic pendulum.
Yes.
We are looking at ballistic pendulum, and we said a ballistic pendulum is a type, because when you talk of a pendulum is something that can swing. Okay, this is the pendulum. Okay, but when
Yes.
we attach a block to it, it now become a ballistic pendulum. It become what we call a ballistic pendulum. So anything that can swing is a pendulum. If you attach a bob on a pendulum, that's why we call it a pendulum bob. But the string alone is what we call a pendulum. The string alone, this string here, alone here, is what we call the pendulum. But attaching now the block on it, this block can be a bob, can also be a what? A bob. Okay? Are you together? So when you attach it now to it, we call it a ballistic pendulum. But
Yes.
it's a ballistic in a context that it does not, after collision, the block, the bullet or the pendlet will get embedded onto the block or onto the bob. They will now move with a common velocity. So this one is before collision and this is after collision. So we are saying let the mass of the bullet or of the pendlet be small m. So you are firing the gun and the bullet is moving with a velocity, with the initial velocity what? U. Is moving with the initial velocity what? U. The block is at rest, is just suspended here. The block is just suspended here, is at rest, and we're saying let the mass be capital M, so that we separated them. You can make this one M1, you can make this one M2. It depends on how you want to make it to be. Okay? You can make this one to be, you can make the mass of the bullet to be M1, then this one become M2. There's no problem with that. Are you together, members? Are we together? Yes, as long as they are
Yes.
well defined. So after impact, now the bullet, because remember you have fired the gun, so which means it will start what? They start swinging. Swinging. So in the process of swinging, because remember they are together, they will be possessing momentum. They'll be possessing what? Momentum. And because now they are embedded together, they will move with a common what? Velocity v. So which type of collision is that? That is it inelastic collision. But we are saying in a process of it swinging, is moving to a given height above the ground. The what? The ground. Okay. So how can we account for this height? We have to account for this height. How can we account for it? How can we account for it? The only way we can account for it is by resolving the component of the length L. Remember, if you compare from here, from here to here, we said is the length L, not so? So when you fire the bullet, it will move to a given height. It will move to a given what? To a given height. So how can we calculate this height? So we find that the component of this L, when it's in space, when it's in an air, is going to be L what? L cos theta. So you find out the whole length L here is going to be the same as L cos theta plus the height, which we put it here now. We are resolving it along so that we find the what? We find this. Okay? So H will be equals to L minus L cos theta. So H is equals to L into L minus cos theta. So when L is common, because this length must remain constant. This length must remain constant. That's why we are saying momentum is always conserved, because this length must remain constant. And we are talking, for momentum to be conserved, we are only considering the horizontal components. We are only considering the horizontal components. So that's why we came here and said, ballistic momentum illustrates the law of conservation of momentum and mechanical energy. And mechanical energy is equal to potential energy plus kinetic energy. So what happens during collision? Momentum, mechanical energy is not conserved. Why? Because there's other external forces acting on it. Because during collision here, you can't establish. There will be no momentum here. There will be no potential energy at this point, because the object is at rest. The object is at rest, which means kinetic energy also is zero. But after collision, we can establish momentum is conserved and kinetic energy is also going to be conserved. Why? Because the object is now moving with a given velocity v. Okay? Are you together, Brenda? Are you together now, Brenda? Brenda, are we together now? Brenda, can you hear me, please? You asked me a question. Have I responded to you, Brenda? Yes? Brenda, can you unmute and talk?
Yes, teacher.
All right. Brenda, your network used to be fine. What happened? What has happened today? You have changed locations. Brenda, your network is not okay. All right. But I believe I've answered you. What about in the process of swinging? What happens? We have seen during. What about after? After collision. That is it when it's swinging now. When it's swinging. Okay? When is what? When it's swinging. So we are saying when it's swinging now, momentum energy is what? Mechanical energy is it? Mechanical energy is what? Conserved. Here, mechanical energy is it? Sorry, mechanical energy is conserved. Mechanical energy is conserved because both kinetic energy and potential energy can be calculated during, after collision, when it's swinging. When is what? When it's swinging. Good. That is it. Then momentum is not conserved. Momentum is not conserved when it's swinging, members. Why? Because why? When it's swinging, why are we saying that momentum is not conserved? Momentum is only conserved in a horizontal direction. Because when it's swinging, it's swinging in a vertical direction. It's swinging in a vertical what? Direction. So here, linear momentum is not conserved. Is not conserved because the pendulum is swinging in a vertical direction, or in the vertical plane. Is swinging in a vertical plane. Is swinging in a vertical plane or vertical direction. In a vertical direction. where external forces are exerted, where external forces are exerted or is acting on the system, full stop. That's why momentum will not be conserved in a vertical plane, So if if energy is conserved, so we said from the principle of conservation of energy, of mechanical energy, which means potential energy is equals to the kinetic energy. So potential energy lost is equals to kinetic energy gained. But we know that potential energy is given by, remember this one is during, when it's swinging. So which means we are going to use the combined mass. This is going to be given capital M plus small m GH. I believe you still remember that, because potential energy, we said is given by mgh. That's potential energy, equals to kinetic energy, which is given by a half into m plus small m v squared. So now what do we need from here? So you see that this one, they are common. So which means this will cancel out that. Then we remain with GH equals to a half V squared. So another way I can find the common velocity V. So if I make the common velocity V squared the subject, you find out I will have 2GH. So which means V is equals to the square root of 2G H. Are we together, members? Are we together on that? Members, are we together on that? Baptist?
Yes, teacher.
Are we together?
Yes.
So what does it mean? This one tells us that the velocity, the combined velocity does not depend on mass. Does not depend on what? On mass. What does it depend on? It depends on, members, what does it depend on? It depends on acceleration due to gravity, and then what? The height.
On the gravity.
On the gravity, and then what?
Gravity and the height.
And the height.
Yes.
Yes.
The height.
Yes. Take note of that. So that's our velocity. If they ask you to find the velocity during the swinging, it's still that. But I can manipulate the formula. What if I don't know the height? What if I don't know the what? The height above the ground level. I can manipulate it. Remember we said but the height h is equals to what? Is equals to L into 1 minus what? Minus cos theta. Do you remember that? Members, do you remember that? So which means now if I substitute that, which means now we can also have a formula also V will be equals to the square root of 2G into, now I have L into 1 minus cos what? Minus cos theta. So I use this one if I know the height above the ground. I use this one if I know the length of the string. If I know the length of the what? Of the string. Okay? So we said where theta is the angle of swing. Members, are we together? Members, are we together?
Yes. Excuse me, sir.
Yes, please.
Yes.
Sir, can I take a look at the previous page?
The notes or my writing space?
Your writing space.
This one here? This one?
Yes, so I was still taking down this part of the notes.
Okay, okay. Baptist. Baptist? Okay. Brenda,
Yes.
Nakachwa? Nakachwa?
Yes, teacher.
Are we together, Brenda?
Yes.
Brenda, where you are, your network is very stable. Don't move an inch.
Okay.
Where you are is very clear. So
Thanks,
members.
I'm done.
Okay. So there's nothing much. That's all about a ballistic pendulum. And it's a very common question. Please take note of it. It's a very common what? Question. It's a very common question. So we can go on and on and on. So we can discuss what are the factors that affect the angle of swing. What are the factors that affect the angle of swing, like you have seen? So factors on which the angle of swing depends on. One, we have the speed of the bullets, not so. The speed of the what? The speed of the bullets or of the petlet. So then the second one is the length L, the length of the string. The length of the what? Of the string. So members, I don't need to again to derive this. I think from here you can find the angle. You can find this angle. And takes note of them also to show that. Okay? So let's write a sample question on that. Sample question. Given that the length of the string L, given the length of the string L, and a bullet is fired at a speed of u before impact, and move, and the system move with a common velocity v, after impact, for a system of ballistic pendulum. Pendulum. Full stop. Show that the angle of swing, beta, is given by or is equals to cos inverse into 2L, 2GL minus V squared over 2GL. Okay? Are you together, members? Are you together? Then they will put for you there 5 marks. That one can carry 5 marks. So where are you going to start from? Members, where are you going to start from? You start working from the first principle. You start from here by sketching this. You sketch this. You sketch this here. You don't need momentum. You come straight to conservation of energy, which is here. From here. I think that. So after reaching here, now you play around with the formula. So just a matter of making cos theta the subject. Now for this case, they've given us the angle of swing is beta, not theta. So in your sketch, you should put what? You should put what? Beta. Are you together, members? Are we together? Members, is that clear? We can answer that question, right?
Yes.
Members, we can answer that question, right? The answer is got from here. I think this one here, this one I'm highlighting here, is from there. So just a matter of making cos theta the subject. Just a matter of making cos theta the subject. Just a matter of making cos theta the subject. So just say from, let's just say from, for this case, I'm just going to take a shortcut from v squared equals to 2gh. From v squared equals to 2gh. But h is equals to L into 1 minus cos theta. Now, because now the angle is beta, so which means this one will change to beta. Okay? That one will change to beta. So substitute it back. So which means I have v squared equals to 2g L into 1 minus cos beta. So just a matter of making cos theta the subject from here. So can you expand that? So we shall have v squared equals to 2g L minus 2g L cos what? Cos beta. Collect the like terms. So when you collect the like terms, we shall have 2g L cos beta is equals to v squared minus supposed to be 2gl minus v squared because I'm taking this one and then I'm taking that on the other side. So 2gl cos beta is equals to 2gl minus v squared. So divide all through by 2gl by 2gl. So this and this will cancel that. Now you remain with cos beta is equals to 2gl minus v squared over 2gl. Okay? So sometimes they can also confuse you. You can distribute the LCM. So we can also say cos beta is the same as 2gl over 2gl minus v squared over 2gl. So this and this will vanish. So remain with cos theta equals to 1 minus v squared over 2gl. I think that, members. Okay?
Yes.
Remember? Yes, that's how you should approach that question here. So to get the cos, to get beta, you know what to do. You just get the aka cos of that. So beta is equals to aka cos of 1 minus v squared over 2gl. So we have 5 minutes remaining. And we are through with ballistic pendulum. And this marks the ends of what? Of linear momentum. This marks the ends of linear momentum. So what we are going to do, okay? We are going to do some questions now. Let's go and do some questions, examples. Question number 1 is there. Can you write that question down? Put that question down. A bullet of mass 50 grams is fired horizontally into a block of wood of mass 8 kilograms, which is suspended by a string of length 2.5 meters. After collision, the blocks swing upwards through an angle of 30 degrees. Calculate the velocity of the bullets, assuming that it gets embedded in the block just after collision. Which means it's going to form a ballistic pendulum. It's going to form a ballistic what? Pendulum. So can you work it out? Can you work it out? So just like we have sketched, I don't need to repeat that. But for you, when you are answering the question, you have to draw from it like exactly you are seeing on the screen, the way you are seeing on the screen. So the mass of the wood, capital M, was given to be 8 kilograms. Then the small m, which is the mass of the bullet. So I can call this one MB. Or I can call it M1. Depends on how you want to call it. Okay? M1. So this is 50 grams, but you have to change it to kilograms. You have to change it to kilograms. 50 divided by 1,000, which will give us 0.0 what? 5 kilograms. Like that. The rest are normal. The rest are like we have discussed. The height, then the momentum. Then for you to find, we say that when it's swinging, kinetic energy is conserved, but the momentum is not conserved. Just like that. Just like that. Like I've said, velocity does not depend on the what? Members, does not depend on the mass. Velocity depends on the height, and because we say the common velocity v is equals to the square root of 2g h is equals to 2g h. Velocity is equals to 2v h. 2v h. Are you together, members? Are we together? Are we together? Yes? Brenda? Brenda? Yes, Baptist?
Yes, teacher.
Are you doing the calculation? Are you doing it? Are you putting it down? Put it down, please. Put it down. Put it down. Put it down, please. So you can get the height. You can get the height. We know how to get the height. We say the height is given by height is equals to L into 1 minus cos theta. And the angle was given. So theta was given to be 30 degrees. Theta was given to be 30 degrees. So which means our height V will be equals to the length which was given to be 2.5 meters into 1 minus cos of 30 degrees. Sorry, so this is the height. So our height will be, so 1 minus cos 30, what do you get? Times 2.5. You get 0.0349 meters. This is to 4 dp. I said our answer must always be to 4 dp. Okay? So that's the height. So that's the height. That is the height. So we can go ahead and find the velocity v. We can go ahead and find the velocity. We can go ahead and find the velocity v. So which means v, the common velocity, will be the square root of 2 times 9.8. 9.8. G is 9.8 times the height, which we have just got 0.3